Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where I am trying to help you to achieve the dream 60 out of 60 in physics in KCET 2025 exam. And we are discussing all the chapters concept wise, and then we are also solving the previous year questions from that chapter. And today we are going to discuss the part 2 of semiconductor electronics chapter. Okay, we have already completed the part 1 of semiconductor electronics chapter. If you have not watched that, you can go to our channel and watch that video. I will share the link for playlist at the end of the video. But if you want to participate in our weekend KPL program, or you want to download the notes that is given after end of the lecture, that you can go to our WhatsApp channel, and don't forget to subscribe to our WhatsApp channel, follow the WhatsApp channel, so that you get the update as soon as we are posting one video. List of content for today is intrinsic semiconductor. We will start with intrinsic semiconductors. We have already discussed what is a semiconductor, what is a conductor in terms of band theory, so I hope that is clear in your head. Now next we will discuss about concepts of hole, very important thing. Okay, then we will discuss extrinsic semiconductors, and then we will discuss n-type semiconductors and p-type semiconductors. So this will be our end of the lecture. Then we will discuss start from p-n junction, diode, etc. We will discuss in our part 3 of the lecture. Now let's start with intrinsic semiconductor. What is the meaning of intrinsic semiconductor? So naturally occurring elemental semiconductors, germanium and silicon, are called intrinsic semiconductors. Okay, so naturally occurring the elemental semiconductors, we discussed yesterday that what are elemental semiconductors, right? So elemental semiconductor means which are found as a element form. Okay, you can take the compound, you can extract the element from it, and if it is a natural semiconductor, then they are called elemental semiconductor, right? So they are intrinsic semiconductors. Okay, the crystal structure, also called the lattice structure. Sometimes you might find that they are being called as lattice, sometimes you might find they are being called crystal. They are same. Okay, in a little bit difference between lattice and crystal, but for your class, for your standard, it is same. Lattice and crystals are almost same meaning, right? Now silicon and germanium are shown here. So let us see the structure of silicon or germanium. Both have tetravalent, that is their valence is 4. So now what is happening is one electron, every one of them has 4 electrons, right? So 4 electrons. So what? So let us consider the central atom. Okay, this is a central atom having 4 extra electrons. What they are doing, they are sharing these electrons with the 4 next nearest neighbors. Okay, so they are not forming bonds with only 2 or only 3. They are sharing the 4 extra electrons with 4 neighboring silicon. So this is one silicon, it is giving 1 electron. Okay, and this one is giving his 1 extra electron of his, and they are forming a bond, a covalent bond, right? We know that covalent bond is when each atom shares 1 electron with each other, so that is called covalent bond. So in covalent bond, each of them should share 1 electron, and that is what is happening here. So they are forming one covalent bond here, another covalent bond here, another covalent bond here, and one more covalent bond here. So they are forming 4 covalent bond with 4 next nearest neighbors, right? Now we know that silicon and germanium have 4 valence electrons. Every silicon or germanium atom share one of its 4 valence electron with each of its 4 nearest neighbor atoms. Nearest neighbor means just next to it. Okay, so for example, if you are studying in a class, okay, your next neighboring class is whoever is just after you or just before you. They are your next neighbors, right? Similarly, for silicon also, this is the next classroom, this is the up classroom, this is the bottom classroom, and this is the before classroom, right? So right, left, top, bottom, so they are the next neighbors. So they will share the electrons with them, and they will form a particular structure, and this particular structure is called lattice. Okay, so this particular structure is called a lattice. It is generally for elements. Now these shared electron pairs are referred to as forming a covalent bond or simply a valence bond. Okay, covalent bond or valent bond, though both are same. So valence band, so because we have talked too much about valence band, so we are saying this bond is valence bond. Okay, so these are the valency bond because its valence is 4, so it is forming a structure with its next nearest silicon atoms. Now let's see what happens. As the temperature increases, more thermal energy becomes available to these electrons, and some of these electrons may break away, becoming free electrons. Very important, becoming free electrons, contributing to the conduction. Okay, so these electrons, because of the thermal agitation, it is called thermal agitation. Because of the thermal agitation, one of such electron may become free, may break free from its lattice, and this may be giving rise to the conduction. Because for conduction, what we need free electrons, okay, which are not bound by any band or any bond, and those electrons should be residing in the conduction band, right? So valence bond is basically where the valence band resides. Okay, now if one electron comes out of the valence band and it moves to the conduction band, that is, it is actually breaking apart from the bond and it is becoming free. Okay, those electrons are actually contributing towards the conduction of the current. The thermal energy effectively ionizes only a few atoms in the crystalline lattice and creates a vacancy in the bond. So what is happening? Once that electron is out of the bond, obviously, so there was a bond, right? So there was a bond, each of them are sharing one electron. Now suppose this electron comes out, these electrons comes out of the bond, then what will happen? This electron is no longer here. So basically what you can say, there is a vacancy. Okay, one electron and one vacancy. Okay, the concept of vacancy is very important, we will see in a while, right? The neighborhood from which the free electron with charge minus q has come out leaves a vacancy with an effective charge of plus q. Because you have taken out this plus minus q charge, there will be a vacancy of equivalent amount of plus q. Why? Because there was a bond, right? So bond requires 2 electrons, right? But you have taken out one of that electron. So if you take out one of that electron, that bond will always try to acquire one more electron from somewhere else, right? So that's why it will have a positive charge, equivalent positive charge. It is not actually a real positive charge, it is only a vacancy, and that vacancy will try to acquire electron from outside, and that's why it is called a equivalent positive charge. Okay, this vacancy with effective positive electronic charge is called a hole. So hole means the lack of electron. Hole means lack of electron. If there was one electron, there would be no holes, but because this electron is out, now that space which is left behind by the free electron, that space is called as holes, right? So this is the basic concept of holes. Holes are nothing but vacancy created by electron which come out of the bond. So here we can observe that there was one bond, okay, and one electron come out of that bond, and then there is a vacancy created, and this vacancy is now we are calling it as hole. Okay, this vacancy is hole, and it will try to acquire electron from its neighbors, and that is why this has a effective charge of plus 1 e or plus e. Okay, so it does not have any mass, it does not have anything, but it can acquire one electron from neighborhood. That's why it is an equivalent of a positive charge. You should remember, this is an equivalent of positive charge. Hole itself does not have anything in it. It is only because the crystal always try to stay in stable condition, the bond always try to stay in stable condition, and that's why it will try to take electrons wherever it is available. That is why this is called a hole. Okay, now the hole behaves as an apparent free particle with effective positive charge. Now why it is apparent free particle? Because as I said, so there is a hole, right? There is a hole. It will try to acquire, suppose there is another bond here somewhere, okay, with electron. What it will try? It will try to acquire this electron, Okay, once the electron transferred from here to here, what will happen is the hole, this will now be filled. This one will now be filled. There is no longer any hole, but this will be now a hole. So hole can transmit from one place to another via transmission of electron. Okay, only electron is moving. Okay, but you can consider that the hole is also moving. Okay, if you ignore the transmission of electron from here to here, the hole itself is moving. So the hole can be treated as a independent, free, positive, effective positive charge. Okay, now in intrinsic semiconductors, the number of free electrons Ne is equal to the number of holes NH. Very important line, right? Number of free electrons. So how many electrons are being freed? Suppose 10 electrons are being freed from the bonds, some throughout the crystal. So if there are 10 free electrons, those electrons coming out of the bond, right? So there should be 10 equal amount of holes, right? So inside a intrinsic semiconductor, the number of holes should be equals to number of free electrons. This is for intrinsic semiconductor. That is Ne equals to NH, and that we are calling that is Ni. Very important term. We will use that in numerical problems as well, where Ni is called the intrinsic carrier concentration. Carrier concentration means it is the charge per unit volume. Okay, charge per unit volume is called charge concentration or carrier concentration. Which one is carrying current? Here electron can carry current, holes can carry current. So that is why it is called intrinsic carrier concentration. Very important term, right? The total current I thus in the sum of the electron current and the hole current. So if there are some current flowing in the circuit, there will be two parts, two things which will contribute towards the conduction. First of all, electrons obviously, and there will be holes as well. Okay, one of them will be positive, one of them will be negative. Now based on the electric field applied, etc., they will vary, but total current will be I is equal to IE plus IH. Very simple concept. Let us look into one question that came in 2020. A positive hole in a semiconductor is absence of free electrons, an artificially created particle, okay, an antiparticle of electron, okay, a vacancy created when an electron leaves a covalent bond. Now you say what is the correct answer? Answer is very obvious. So you can see that the only question that you might think between A and C. Now A is absence of free electrons. Absence of free electron does not give you holes. Okay, for example, insulator does not have any free electrons and they don't have any holes either. But when an electron leaves the covalent bond, it leaves a space behind. That space can be considered as holes. Okay, so basically it is a vacancy created when an electron leaves a covalent bond. So if you see all the options, you can guess, okay, this is the longest option, this should be the answer. Not always, but in this case it is true. Right, now let's look into the homework problem I gave you yesterday. Okay, the forbidden energy gap for germanium crystal at 0 Kelvin is. So what is the forbidden energy gap for germanium? So if you have done your research, it will be 0.71 electron volt. We will discuss that in a while, but since we have discussed about forbidden energy gap, so forbidden energy gap for germanium is 0.71 electron volt. You should remember that value. Okay, the energy gap in case of which of the following is less than 3 electron volts but greater than 0? So as we discussed, so energy gap for all the metal should be 0. Okay, so aluminium is 0, iron is 0, copper is 0. So only for germanium it is less than 3 electron volt but greater than 0. It is not 0, as we have seen it is 0.71 electron volt. Okay, in the previous question itself we have seen that it is 0.71 electron volt. So this for other metals it is always 0. Okay, now let's look into the extrinsic semiconductors. So far what we have studied, intrinsic semiconductors, they have equal number of holes, equal number of electrons, right? Now the conductivity of an intrinsic semiconductor depends on its temperature. So what you have to do, suppose I have created a semiconductor device, something, okay, a camera, which based on only intrinsic semiconductor. Okay, it has a chip. Chip has a semiconductor. Now what to make it function, what I have to do, I have to keep it inside a heater or a fire. right? For example, a mobile phone developed using this technology. Suppose I have developed a mobile phone based on the technology of intrinsic semiconductor only. Then to make it function, what I have to do, I have to put a lamp behind it always to make it work. Okay, even the heat generated in the process of the mobile phone is not sufficient. You have to have a extra heater under the mobile phone, so it will be always hot. So that is not desirable, right? So to make it function in normal temperature, normal room temperature, intrinsic semiconductors are not good. They are not at all helpful, okay? Maybe in some cases it is helpful, but 99.99% cases it is not at all helpful to always have a heater to make it operational, right? So what we have to do, we have to find a way to make it operational in room temperature. So depends on the temperature, but at room temperature its conductivity is very low. As I said, the conductivity of semiconductor is very low in room temperature. To make it work, we have to use a heater, which is completely impractical, not possible at all. So as such, no important electronic devices can be developed using these semiconductors. So as I said, I wanted to develop a device, but practically it is not possible because you cannot always move with a heater in your hand. Okay, better then the price of the heater will be more than that of the semiconductor device, right? So what we have to do, hence there is a necessity of improving their conductivity. Okay, how can we improve their conductivity? This can be done by use of impurities. So sometimes we say that there are impurities, it should not eat if there is impurity, but sometimes impurities are good. One such example is this process, this semiconductor, extrinsic semiconductor. Impurities are not always bad. There is an exception where impurities are good. That is when you are using a semiconductor device and it is must to have impurities. Without impurities, semiconductor has no meaning. Right? So when a small amount, say a few parts per million means if there are 1 million atoms, okay, 1 million means 10 lakhs. Okay, 1 million means 10 lakhs. Okay, so suppose there are 10 lakhs of atoms and if you impart say 2 or 3 impurity atom, okay, that is the level of impurity that we are talking about. So very small amount of impurities, okay, few parts per million, ppm. If you may have heard the term ppm, which is very common in some measurement, okay, for a suitable impurity is added to the pure semiconductor, the conductivity of the semiconductor increases many-fold. So if you add suitable impurity, okay, depending upon the usage, this level of impurity addition varies from depending upon the level of application. But if you in general, commonly if you add say a few parts per million, that means 1 or 2 atoms per 10 lakhs atoms, then it is a suitable object. So basically you are adding a very small amount of impurity. It's not very high, right? So 1 in 10 lakhs means 10 to the power of 5. So up to 10 to the power of 5 or 10 to the power of 6 atoms, you are adding only 1 or 2 impurities. So that is the level of impurity addition. Okay, such materials are known as extrinsic semiconductors or impure semiconductors. Obviously they are not 100% pure because you have added impurity, so that is why they are called extrinsic semiconductor, where you are forcing it to be a semiconductor, and also sometimes they are called impure semiconductor. Okay, now what type of dopants, what type of things that we will add? So let's learn about that. The deliberate addition of desirable impurity is called doping. It is very common in sports. If you are following any Olympics or anything, you might have heard that that person was caught doping. Okay, because doping means something, a foreign substance that you are taking to improve your performance. Okay, so basically doping is something which improves the performance, but it is not natural. You are taking it externally. Okay, so extrinsic semiconductor comes from the term external. So that's why it is called doping. Doping is something which improves its performance, right? So doping, the addition of impurity is called doping, and the impurity atoms are called dopants. Okay, So dopants means something that you have added to improve its performance. Okay, such material is also called doped semiconductor. So semiconductor itself is called doped semiconductor. Okay, so doped semiconductor, extrinsic semiconductor, impure semiconductors, they are all but same. There are two types of dopants used in doping the tetravalent silicon or germanium. So valency of silicon and germanium are 4. So we can add two types of dopants. So let's see what are those. Pentavalent dopants. Pentavalent dopants has a valency 5. Penta means 5, right? So pentagon, 5 arms. Similarly, pentavalent means valency 5. So what are those materials? You have to remember one or two examples. In exam, maybe they might ask you what is the type we will dope to get certain material. We will discuss that. But you should remember that arsenic, antimony, phosphorus, these three are very commonly used pentavalent dopants. Okay, so arsenic, antimony are brothers. Okay, bismuth also, maybe you have heard about bismuth. Okay, arsenic, antimony, bismuth, phosphorus, they are pentavalent dopants that we might use. Next is trivalent. Trivalent is valency 3. Right, so what was the valency of silicon and germanium? Silicon and germanium has valency 4. Right, now what are the two types of dopant we can use? We can either use pentavalent, that is 1 more than 4, or we can use trivalent, which is 1 less than 4. Okay, they both play important role. We will see that. Examples are indium, boron, aluminium, etc. Now I hope that you remember that boron and aluminium has a valency 3. Indium is something new. Okay, I hope you will try to remember that as well. So indium, boron and aluminium are the examples of trivalent dopants. Now let us start about N-type semiconductors. So first of all, we discussed that two types of dopants we can use, either pentavalent or trivalent. Now what will happen if we dope it using pentavalent? Okay, let's discuss that. So suppose we dope silicon with a pentavalent element. Say we doped silicon with a pentavalent phosphorus. Now when an atom of +5 valency element occupied the position of an atom, okay, in the crystal lattice of silicon, 4 of its electron bond with the 4 silicon neighbors, while the 5th remains weakly bound to the parent atom. So what happens is that, because suppose you went to a fair, and in the fair everyone is having wearing a cap, but you don't have a cap. So what you will do? You have 2 caps. Okay, everyone is having only say 1 cap wearing. So what you will do? You will wear 1 cap and you will keep 1 cap extra in your hand. Okay, so and sometimes someone without a cap appears, he will take that cap away. Right, so this is easy to take away this extra cap that you have in your hand, right? But if you are wearing both the caps, then it will be difficult for someone to take both caps away from your head. So you are wearing, this is just an example. Okay, so you are wearing caps in a fair, but you have 1 extra cap that you are holding in your hand, and that is almost free, right? So similarly, because silicon, everywhere in the silicon neighborhood, everyone is having 4 electrons with their neighbors, right? Also silicon can accept only 4 electrons, right, from the neighbors, 1 from each. Now phosphorus has 5. So what he will do? He will lose 1 electron, he will give away 1 electron, or he will say, okay, stay here, I have only 4% to go inside, but you are 5th one, you stay outside. So he will take 1 electron, he will keep it outside, and he will bond amongst all the silicons, and he will behave, okay, I am a silicon. Okay, I am just like a silicon. That extra electron will stay outside. Now that extra electron will be, for example, if you see, there is a pentavalent phosphorus, okay, and we have all tetravalent silicon around. So what he has done? He has bonded with 1, 2, 3, 4, 5, 6, 7, 8 electrons, right? 8 electrons in the outer shell, that is the stable orbit. So he has taken 4 bonds, that is, it has now 8 electrons, but this is a 9th one. So what he will do? He will say, okay, you stay out of this. Okay, he will leave it alone. Okay, this is almost free electron. This is almost free electron. Why? We'll see that. This is because the 4 electrons participating in the bonding are seen as the part of the effective core of the atom by the 5th electron. Okay, so he will see, okay, I am the adopted child. I am not the part of the family, because till now he was carrying me, but now as soon as he saw the family, he left me out. So I am just the adopted family. So what he will do? He will rebel against the family, right? So as a result, the ionization energy required to set this electron free is very small, and even at room temperature it will be free to move. So even at room temperature it will be free to move, and he will say, I will do whatever I want. Right? He will say, I am the rebel, I am the adopted child, I will do whatever I want. So just jokes apart, don't take it seriously. Right? Now, the energy required is almost equals to 0.01 electron volt. As you see, 0.01 electron volt is very, very small energy. Right? 0.01 electron volt is very small energy. 1 electron volt is 1.6 into 10 to the power of 19 minus 19 joules, right? So 0.1 electron volt is very small energy for a doped germanium, and 0.505 electron volt for a doped silicon. So to make free, suppose you have doped phosphorus to a germanium, then the electron which is attached to that germanium crystal, the free electron, that you need only 0.01 electron volt to make it free. Okay, if the atom is silicon, if the crystal is silicon, base crystal is silicon, then you need just 0.05 electron volt to make it free. Okay, now this contrast with the energy required to jump the forbidden band about 0.72 electron volt. So I said I will discuss it. So 0.72 electron volt is for germanium, and about 1.1 electron volt for silicon. Now you should remember this 1.1 electron volt. Okay, because previous year they have asked about the band gap of forbidden energy gap of germanium. Now next year, this year, they might ask you what is the forbidden energy gap for silicon. Now let's move on. Semiconductor doped with pentavalent impurity, electrons become the majority carriers and holes are minority carriers. So in case of intrinsic semiconductors, we have seen that the number of electrons is equal to number of holes. But when you dope it with a pentavalent material, then what happens is that the electrons are more. Obviously there are more free electrons, one free electron per doped element. Okay, now we know that material has a lot of number of atoms, so even if you dope it with very small amount, still the number of free electron is very high, right? So now those electrons are extra. Those electrons are other than that of already existing electron hole pair. They are being called electron hole pair, which is generated by thermal agitation. Okay, so because of the thermal agitation, there are some electrons developed, but these are the extra electrons. So total number of electron is now more than the total number of holes. Okay, these semiconductors are therefore known as N-type semiconductors. N means, N stands for negative. N stands for negative type. Negative means electrons are more, and that is why they are called negative type semiconductors or N-type semiconductors. Okay. For N-type semiconductors, we have number of electrons are more than number of holes. Okay, so number of electrons are more than number of holes. Now, P-type semiconductor. Now let us talk about positive type. So you have understood negative type. Now it should be easier for you to now understand the positive type or P-type semiconductor. This is obtained when silicon or germanium is doped with a trivalent impurity, right? Now what happens? The dopant has one valence electron less than silicon or germanium, and therefore this atom can form covalent bonds with the neighboring 3 atoms, but does not have the electron to form the fourth with the fourth silicon atom. So what is now? You are visiting the same fair. Okay, in that fair everyone is wearing cap, but you don't have the cap. Then what you will do? You will take cap from someone somewhere, and then you will wear it and you will hide. You say I also have a cap, then you will walk away. But the cap that you have stolen, he will also think, okay, where is my cap? I will take cap from someone. So this way there are more number of empty heads compared to more number of caps, right? In the previous case, we had more number of free caps compared to more number of heads, right? Now here we have more number of empty heads, that is people are not wearing caps compared to more number of people having caps, right? So here we are creating an artificial hole. Okay, so there is a lack of electron present in the bond, and that is called extra number of holes. So the bond between the fourth neighbor and the trivalent atom has a vacancy or hole, right? Extrinsic semiconductors doped with trivalent impurity are called p-type semiconductor because it has extra hole, and we know we are calling holes as p-type or positive type, so that is why they are called positive type semiconductor or p-type semiconductor. Okay, for p-type semiconductors, number of holes is obviously more than number of electrons, much more than number of electrons. Now this is very important. This is common for p-type and n-type. This is common. This point is common for both p-type and n-type. Note that the crystal maintains an overall charge neutrality. Okay, overall charge neutrality, as the charge of additional charge carrier is just equal and opposite to that of the ionized cores of the lattice. So for example, phosphorus, when you doped with the phosphorus, it has pentavalent, yes, it is a pentavalent material, but pentavalent means it has equal number of protons inside its nucleus as well. Whatever total number of electrons, total number of protons are also there inside the nucleus. So even though one electron is coming out of the outer orbit, okay, that is from the valence band, one electron is moving to the conduction band, but the total number of positive charge is still there, equals to the total number of negative charge. Hole and electrons number different, okay, but total positive charge is equal to total negative charge always. Okay, in extrinsic semiconductor as well. Okay, we will study in our next lecture, we will study about p-n junction as well. Everywhere the total number of charge is 0, even though there are mobile carriers. There are charges which are free now, they can move to carry external current, but internally they have a charge, they are charge neutral, very important. So that is why if you touch a diode or if you touch a semiconductor, you will not get electric shock because they are electrically neutral, very important. Okay, now the electron and hole concentration in a semiconductor in thermal equilibrium is given by, so this is a very important relationship in a doped semiconductor. This is very important relationship. Okay, in Ne times Nih, okay, this is not Ni, Ne times Nh equals to Ni square. Now what is Ne? Ne is hole concentration, Ne is electron concentration when you have doped. It is valid for both n-type or p-type. Okay, so when the total number of electrons in that lattice, in that crystal, suppose that is Ne, free electrons obviously, and total number of holes is Nh. Okay, and when the semiconductor was in intrinsic condition, okay, when there was no dopant, in that case, suppose its concentration, charge concentration was Ni. You remember that we have we wrote that Ne equals to Nh equals to Ni for intrinsic semiconductor. Right? So for intrinsic semiconductors, Ni was equals to Nh. Both of them are equal. So Ne Nh is equal to Ni square, obviously true for intrinsic semiconductor, but for extrinsic semiconductor as well, this relationship is true. And there was one problem came from this concept. Let's see this concept. The density of an electron hole pair in a pure germanium is 3 times 10 to the power of 16 meter inverse, meter cube to the power minus 3, meter to the power minus 3. So Ni is given here. Ni is given here 3 times 10 to the power of 16, right? So this is basically Ni, right? Now on doping with aluminium, okay, doping with aluminium means what type of semiconductor it is? Tell me. When you dope with this aluminum, it will become aluminum is a trivalent material, so it will be a p-type semiconductor. Okay, on doping with aluminum, the hole density increases to 4.5 times 10 to the power of 22 meter cube. So now hole density is 4.5 times 10 to the power of 22. Okay, now the electron density is, so we know that Ne times Nh equals to Ni square. So this is always true. You have to remember that it is always true. So what is Ne? We are trying to find Ne. So Ne is Ni square divided by Nh. Okay. So what is Ni? Ni is 3 times 10 to the power of 16 whole square divided by 4.5 times 10 to the power of 22. Okay, so what is 3 times 10 to the power 16 whole square? So Ne will be equals to, this is 9, 3 square is 9 times 10 to the power of 16 square is 10 to the power of 32, 16 to the 32, right? And then 4.5 times 10 to the power of 22. Okay, so it will cancel, it will become 2. So it will become 2 times 10 to the power of 32 minus 22, that is 10. So the concentration of electron is now 2 times 10 to the power of 10. Simple problem. Okay, this is from one of your previous year, I think 2021 or 2020 this question came, and this is a very important question. Why I am focusing on all these questions? Because one major part, as I said, is now deleted, so there is a probability that there will be a question based on this concept, this formula. Okay, so be careful. Now let us look into the homework problem for today's lecture. So these are the homework problem. Try to read this question, answer this. I will be discussing these answers tomorrow's lecture. It's also very interesting question. Okay, read this question, try to answer the question. Be easy question, very easy question. Okay, mention the answer in the comment below. I will reply to you if your answer is correct, and I will discuss the solution in tomorrow's lecture. Okay, now I said, if you have missed any previous lectures or if you want to revise any of the lectures, we have a dedicated playlist in our channel for physics 2025 KCET exam. Okay, you have to bookmark that, and whenever you are getting time, you have to visit that bookmark, read from there, study from there. Okay, download the class notes. So everything is available in here, and all the latest videos are getting uploaded in this playlist. Okay, so don't worry if you miss one lecture, you can visit here anytime. And if you want to participate in KPL, or if you want to download our class notes or any updates related to KCET 2025, don't forget to join our WhatsApp group. The link is given in the description. And if you like this lecture, don't forget to share it with your friends. Subscribe to our channel if you have not yet, and like this video. I'll be back with semiconductor part 3 tomorrow, and then day after we will complete all the PYQs of semiconductor. Till then, bye.